Okay, guys, we've gone over this a couple times in class. The videos on the playlist are a little bit, everything is there. It's not completely in one place, one-stop shopping. So I'm going to go back over basically exactly what I said in class. And because the old videos may have reflected different as I've evolved my understanding of this lab. I've changed what I have students do, so I wanted to just make sure we have the latest and greatest. So I've basically got a spreadsheet file open here, and I've got weights of sleds here as needed, and then I have my two sets of data, concatenated data, and this is where, and this one's constant mass, and this one is constant force, as you see the mass in little m is always the same. And so this is everything I would have had in my logbook. And don't forget, your logbook needs an explanation of where A comes from. It's from the fit of the software on the laptop, and it also provided a plus minus, and in this case somebody typed in plus minus. You can't put that there, so but I changed the masses into kilograms so I could have MKS. It's not essential that you do that. It might make it easier to follow the spreadsheet though. Okay. Excuse me. So we had 5 runs. There's the mass on the that's the mass on the hanger plus the mass of the hanger, although that looks doubtful with these round numbers, but that's okay. It doesn't change the analysis that I'm about to show you. And just see this, if I'm going to divide by 1,000, I have to add some more digits here. Okay, so again, the A and the plus minus A comes from the this capstone software that was running on the laptop. So I just said here, I've turned everything into kilograms, and I've created this column for m plus m, 1 over m plus m, and mg. And similarly here, because in both places we're going to use mg and 1 over. And I remind you that, as always, you start off with an equation, and then we adapt it to our apparatus, and we want to test this thing. So F becomes mg, which is the mass of the hanger and whatever weights we put on it, equals to the total mass, which is that little m, plus capital M, the mass of the sled going back and forth, times the acceleration. Now, in our case, we're changing masses and measuring the acceleration, so we're going to rearrange this equation to be in the same manner that Newton himself originally wrote it. And now we can kind of see where the so-called constant mass and constant acceleration come from. Just making myself a little more room here. These graphs actually are not exactly the right thing. And so you see where if we can now make 2 plots, both of them are going to have acceleration on the y-axis, because that's our dependent variable. And our independent variable, one of them is going to be the mg, with the slope of 1 over m plus m. And one of them is going to be 1 over m plus m. And the slope is going to be mg, because that's going to have a constant force, so that lends itself. So if you would say then A equals 1 over little m plus capital M. That's the slope. Mg is the x-axis. And then here, similarly, we have mg as the slope, and 1 over little m plus capital M is the x-axis. And we'll have error bars, which the plus minus a given us. So we can then use the chi-squared to get us a plus minus on that acceleration. And we can also use the r-squared test to test linearity. So we don't have an accepted value for something like this. So we need to demonstrate to people that they should believe f equals ma. And so the two graphs tell us that the equation is correct depending upon our plus minus a. It should be pretty small. So if we have an acceleration and a plus minus, it's the slopes of these so we'll have our slope and our plus minus slope, and our figure of merit is going to be the plus minus slope divided by the slope and times 100, and we want this to be less than 10%. And then the other figure of merit, which will tell us that we believe these equations, and the r-squared test is the test of the goodness of the fit. And if the fit is linear and we get a 0.9 or better, that tells us that we picked the right fit equation. And one of the assertions of Newton's second law is it's linear in all terms. Nobody is squared. Okay, so let's get to it. So we'll do one of these at a time. And so this one here we'll call this the constant mass. Okay, and that means we're taking the data in this table here, to convert it into what I needed right there. And so let's start off with a graph. So there's our x-axis, our y-axis, and here's our x-axis. So I select it, I hold down the control key, and I can select another column. And I can insert a chart, a graph, and most likely it's reversed. So I have to select data and edit. So this is my A, and now we need this x values to be mg and the y values to be a. Nice. And great. And we'll say OK. And in fact, we can even say A for constant mass. That looks nicer. And let's just format this right away. Wrap text. Great. Now it looks prettier. And we see something a little bit wrong here. I don't remember if this is real data or is this make-believe data. Let's see if I say one, yeah, that makes it a little more room. Okay, so something's not really good with this. Right, I see it. That really should be more. Let's just call it 4 for the fun of it. That makes our graph look a little nicer. Okay, so I'm going to insert error bars now. And remember, to get this gray sidebar, I go click, and I see the chart tools, format, design. And so if we select the data set, make sure they all highlight. And now we add a chart element and want error bars. Let's pick one of them, it doesn't matter. And now if we want to format that, we go to the format, and for Mac users, you have to go up here to this drop down box, and now we put in a fixed value for X error bars as 0. And this also goes to the difference between the original manual and my rewrite, because the original manual had for at least one of these graphs putting A as the x-axis, and that's dumb because the x-axis has got to be the independent variable, the thing that we set, the knob you turn. Okay, so there is our error bars. They're kind of on the small side, but that's okay. So we're going to need our fit. We're going to need our residuals squared. I'm going to skip a step and go straight to residual squared. And then we have chi-square. Let's see if the chi is waiting for us. There it is. That's a lowercase, okay. Chi-square. And then we need the SS squared. And that is the basically the variance, you might recall. Let's see here. Let's wrap. Good. All right. I think that's everything we need. So let's make our fit parameter table. So we have the slope. We have the y-intercept. We have the sum of the residual squared, so we need an insert symbol. No, we don't have it. We need the capital sigma. Where's the capital sigma? There it is. Insert, close. So we need 3 of these. So let's just drag that down. There we go. We double click inside the res squared. Now we need the chi squared. And we need the SS squared. And we need R squared. There we go. And it looks like we can make this a little bit wider just to accommodate that. And let's see what we see. 1, it looks like the slope is about 4. Okay. And we expect, we don't expect the y-intercept to be 0. It doesn't look like. Well, that must mean there's some systematic error here, but that's not the end of the world because we only care about the slope. So it looks like it's going to be about 1.4. Okay, so let's see, format these as numbers. Okay, we're almost at about 15 minutes of video, so I think I'm going to stop this at some point. Okay, so this equals the slope, and then we need our dollar signs times the x value, which in this case is mg, plus the y-intercept, which is there. We need our dollar signs, and there we go. And these need to be formatted as numbers. Okay, and let's see, we'll give it an extra one for now. There we go. And so this equals the data, which is the acceleration, minus the fit, which is here, close it, square it, and then the chi-square equals the res squared divided by the, and I'm just going to be extra careful, the error bar squared. Oh, that's big, huh? And then the SS squared is the variance squared, so that is equal to the data, which is the acceleration. Oh, I forgot the equal sign. Equals, open parentheses, data point, minus the average of the data points. And now we need our F4 key. Yep, because it's always the same average. And then we want to close it and square it. Now we have our SS squared. Okay, now we can just go ahead and fill them all in. This stuff should all be familiar. We've talked about this several times now. We added the R squared into it for this lab. And let's see, and we have, let's put these here, all borders, and we're in. Okay, so let's see, let's see if we can squeeze in most of the constant mass in less than 25 minutes. So we want to select data. Oh, and I realize I need a little more space here. Insert, because I want to add in for the x-axis, which is the mg's, I want to add a 0, because I like my fit line to go past the ends of the data, and I like it to go to the y-intercept as well. I just drag that. Nice, huh? So now I select data, and I add the fit line. And I have my x values, I have the forces, mg's, and of course the y values are the fit line, the fit values. And we say OK. And now we need to edit it, because we want a solid line. And we can go to Dr. Harry's favorite, red, and we want to have no marker, none. Okay, let's take a look. There it is. It's not going through it yet, but we'll get there. Equals sum of the residual squared equals sum of the chi-squareds and equals sum of the SS's squared. And of course, something happens here. Yeah, inserted. Cut and paste. Keep it quick and easy. So this equals 1 minus the sum of the residuals squared divided by the sum of the variances squared, and I think we just hit enter. Something not right. And 1 minus, oh, right. Well, that's because the fit isn't very good. It's a negative number, which is a no-no, but we need to finish the fitting procedure. Let's save it. So we go to data. We go to solver. And we want to minimize the value of the sum of the chi-square. And by moving around the slope and the y-intercept, and we want to undo this one, we solve, ooh, and look at that, we got a great fit. And now our r squared, and it's standard to leave this as 4 decimal places. That's pretty darn nice. So what's left is to do the plus minus slope. I think Jenny has lunch ready, so I'm going to pause this for a little while and I'll be back. Of course, you won't notice any difference. Okay, well, I've been gone quite a while, but you wouldn't know the difference. So we need to get the plus minus on the slope. So we need the sum of the chi-square, which is here. And we need to copy that and paste its value. Paste special. Well, that's weird. Why is it doing that? I thought I was copying. Oh, I must be, right, that was a piece of drawing there. Okay. Copy. Paste number. And we've got ourselves some whatchamacallit, that's decimal places. And yeah, there it is. No. Copy. So what we want, I don't think it's possible. Where is the solver? Okay, I see. So value of control A. Oh, it worked. Oh, there it goes. You can copy paste. Okay, so I want to add 1 to that, so make it a 13. And let's see. Oh my. And it worked. Alright, so now the slope, so this is copy. So that is the slope extreme. And now we want to go back to the original. And we can't hit undo. That doesn't work for some reason. We just want to minimize that. Solve. And there it is. And let's add some decimal places here. Okay, so then the plus minus slope. Let's see, apostrophe plus minus slope equals the absolute value. Just want to know the difference between these two. This minus that. And enter. Okay, great. So let's see now. We have now, let's put our percent error on the slope. And that's going to equal to the plus minus divided by the slope. times 100. Okay, 0.23%. That's quite a small error bar. And we want to know the percent difference. So we expected it to be 3.145. So the percent difference is DIFF tab. That equals the expected value. Let's see, we should put quotes about it just to be safe. So the expected value minus the, and it's supposed to be absolute, isn't it? ABS, and the expected value minus the actual value, and then divided by the average of the two, which is equal, then, let's see, AVERGE, average of this, and comma, this, yeah, and then the whole mass. I guess I'm going to put parentheses around the whole mass, and then I'm going to multiply times 100. Okay. And I don't like that. Let's see. I wanted to put that parentheses there. And yeah. I don't think it didn't change anything. So it wasn't the best in the world, but then again, these, I don't know, I'm suspicious of these data points. Okay, so we have our fit parameters here. One could imagine maybe formatting this a little bit better to make it a little more obvious what's going on. Maybe one doesn't include this part. I just use this as a placeholder. It's not key. And so now this is the constant mass. Okay, so I'm going to stop this and upload it and then make one for the constant force.